It is time to start with the first example of a neural network. The network will exist of one neuron that has a single input and a single output. You might wonder what we can do with such a simple network. Well, here are some examples. A network with a single neuron can learn the relationship between the size of a house and its price, the amount of fertilizer and the health of your plants, or the relationship between the age of a car and the maintenance costs. All these examples model the relationship between one input and one output. But before I show you real-world examples like this, I will show you something that is even more simple. The relationship between x and y values. Look at the points in the diagram. Without doing any calculation, it is easy to see the relationship between x and y. For each x value in the diagram, the y value is doubled. This becomes even more clear when I draw a line through all the points. A line that tries to go through as many data points as possible is called a regression line. It is our goal to find the slope of the regression line. The slope of the regression line will play a huge role in our network, as you will see later. Just by looking at the diagram, we see that the slope of this line is 2. We can write this down as a function, y equals x times 2. This function will calculate the y value for each x value. Or, better said, it predicts the y value for any x value. The challenge is to find the correct value of the slope, 2. In a neural network, of course, the slope needs to be learned from training data. The algorithm to do this is called linear regression. And this is what our first network will use. So what do we have? We know there are 4 points on the line. Here you see their coordinates. We know that the values have some relationship that is determined by something called the slope. Our goal is to find the slope of the line. After finding the slope, we have a function that can compute any point by feeding it an x value. Perhaps you wonder why we need 4 points. 2 points should be enough to calculate a line function, right? That's true in this example, because all points fall exactly on the line. But very soon we will see data where the points will not fall exactly on the line, and at that point, the more data we have, the better the network can be trained. That's why we will use all data points to train the system. It's time to code. Let's make a network with one neuron, one input, and one output. Let me create a new Python file called firstnetwork.py. I start by defining the slope. A common variable name for the slope is w. The computer needs to calculate the slope for us, but we need to start with an arbitrary value. Now I create a function that takes an input and returns slope times input. You may not believe it, but this is already a neural network. I admit, it won't be able to predict very well, but nonetheless, we are well on our way. Let's make a prediction and feed the function with the value 2. The target value for 2 should be 4. Let's execute the code. As expected, the prediction is far off. What you just saw is called feed forward. The neuron took input value 2. The input was multiplied by w and produced output 0.2. This is a working example of a neural network with one neuron. It only has one problem. It is not very good at predicting. It needs to be trained. And this is where the training data comes in. Let's add it to the code. The data points are added, and now it's time to train the network. I will now make a prediction for all the inputs and put the results in variable pred. Pred now holds a list with predictions. The network now needs a way to express how accurate the predictions are. Each target value can be compared with a prediction. The difference between the two is known as the error of a single training sample. I'll create a list with errors for all samples. Then we calculate the average over all the errors. This average is called the cost. It is a single number that indicates how well the network is doing. Let's print the slope and the cost. Notice I am printing slope W and mark it as weight. For our purposes, weight and slope are the same thing. Let me execute the code. When we use weight 0.1, the cost is 4.75. You will get a good understanding of the meaning of this value soon. For now, let's just say the goal is to get the cost as close to zero as possible. That leaves us with a question. How can we make the cost go to zero? It turns out that this is not a trivial question, which we will see once our network will progress. For now, however, let's use the cost value to adjust the only parameter in the network that we control, the weight. I add the cost to the weight. Neural networks learn by repeatedly processing the training data. Let's put the whole thing in a loop to see what happens to the cost after 10 iterations. When I execute the code, the cost should go to zero. As you see, the cost values are all over the place. Let me plot them in a diagram for you. The diagram shows an oscillating pattern, and instead of decreasing the cost, it gets bigger with each iteration. Apparently, the adjustments are too big. To reduce the adjustments, we use something called a learning rate. Let me add it to the code. I'll set the learning rate to 0.01. This is just an arbitrary value to see what happens. I execute the code. Yes, that looks better. By taking small correction steps, the cost gets closer to zero. Now we need to find a good balance between the learning rate and iterations. I'll start by changing the iterations to 20. The cost keeps going down, but it is not close to zero. I'll make the learning rate 10 times larger. Look at the cost. With only 4 data points and 20 iterations, the network is trained. I bet if we increase the iterations just a bit, we get a perfect value for the weight. Very nice. Let me plot the cost for each iteration. This time, the error is gradually going down. Since weight adjustments depend on the cost, the updates are getting smaller as the cost gets nearer to zero. You have seen your first cost function. It is the mean sum of errors cost function. This function calculated the cost like this. There are 4 known targets. There are 4 predictions. Each prediction is subtracted from each target. This results in a list of 4 errors. The list of errors is averaged and out comes a single number. We repeated calculating the average cost 25 times and used it to adjust the weight. Since we only had 4 points in the data, this is no problem for Python. Even with 1,000 iterations, this will still be very fast to compute. But as our examples get more complicated, we will see that we eventually have to choose a different strategy. For now, we're doing fine. Updating the weight in the network is called backpropagation. Backpropagation takes the desired weight changes and propagates it back to the start of the network by adjusting the weights. Since our network only had a single weight, this was the only thing that was adjusted by the backpropagation. Later, this will get more complex. When the backpropagation completes, one training round is complete. The network is now ready to proceed with the next feed forward. So now that we have trained the network, how about making a prediction? Let's feed the network some test data it has not seen before and see how it is doing. I make a list of test predictions. And compare them with the test data. I execute the code. That is very accurate. There is nothing stopping you from training the network more to get an even better result, but I think this is already pretty good. Remember, our goal was not to create a perfect doubling function, but to create a neural network that makes good predictions. There is something I'd like to point your attention to. Look at the code. Each iteration, the predictions are calculated for all training samples. The cost is calculated by averaging the errors of all training samples. And at the end of each iteration, the weight is updated. I repeat, each iteration, all samples are processed and used to update the weight. This algorithm is called batch gradient descent. With batch gradient descent, every training sample from the training data is processed before updating the weight. You will see this algorithm often during this training. Later on in the training, we look at alternatives, but for now, this is what we will use to train the network. Look at this diagram again. It took our network 25 training iterations to minimize the error. We can improve this by using another cost function, and you will see how that works in the next part. Results in some error, which is the difference between the target and the prediction. The cost function averages these errors and produces a cost, which is a single value. We used it to update the weight. This is repeated. A new cost is calculated and the weight is updated. The goal is to minimize the cost. To get the cost as small as possible, we must make the result of the cost function as small as possible by adjusting its parameters. This is called minimizing the cost function. Look at the cost function again. The prediction is subtracted from the target. The prediction is the weight times the input. The function can be rewritten like this. What parameters in this function are under our control? It turns out the only thing we can change is the weight. You saw how this worked in the code. So let me repeat. Minimizing this cost function means adjusting the weight so that the result of the cost function goes down. However, the cost function we have used is not the most suitable cost function for our problem. I just used it because it is easy to start with. But we can do better. It turns out there are many cost functions to choose from. Here you see 4 cost functions. Different types of neural networks solve different problems, and each problem asks for a specific cost function. When I started researching neural networks, I found it very confusing why and when a specific cost function was used. And I don't even want to start about the fact that cost function, loss function, and error function are all used to describe the same thing, sometimes even in a single chapter. There seems to be some consensus that the words loss and error are used for single training samples, and the cost is the average over all samples. But even if they have subtle differences, their purpose is all the same, to indicate how well the network is doing. When I started investigating neural networks, I noticed a certain cost function that was used when dealing with linear regression. It's called the mean squared error cost function. What does it do? It calculates the error of a single training sample by subtracting the target from the prediction and then squares the error. The squared errors of all the training samples are summed and divided by the amount of training samples. The result is a single number that tells us how well the network is doing. As you have learned, we call this number the cost. Squaring the error gives us a logarithmic scale. Large distances result in higher costs, and low distances result in smaller costs. Notice that by squaring the error, the result will always be positive, regardless the position is before or after the target. This poses the question: how do we know in what direction the weight should be adjusted? And here it will get a bit more difficult, but we will run into that problem as soon as we start replacing the cost function by the mean squared error cost function. I replace the current cost function with the mean squared error cost function. Let's see what happens. We get an overflow error. By squaring the errors, the cost is too big to be used to change the weight. We need to find another way to adjust the weight in the neural network. And for this, we need a bit of calculus. Calculus deals with change and motion. To be specific, we look at differential calculus. To find the change to the weight, we differentiate the cost function to get a derivative function. Let me try to explain why we need the derivative function. Look at the cost function. Let's replace p by weight times the input. We know we cannot change I and t. They are determined by the training data. Let's fill in an x and y value for one of the training data points. The weight is the only parameter we can tweak. Let me plot this function for you. The first thing you notice is the ball shape. This is typical for functions that are squared. You also notice that the cost is 0 at weight 2. That is consistent with our training data, where each y value is x times 2. So 2 is where the weight should go to. So what is the cost when the system starts training? We started with weight 0.1. That means that the cost is around 14. But the cost just tells us how well we are predicting. The real question is, in what direction should the weight move to minimize the cost? To answer this question, we need the tangent of this point. And this is where differentiating comes in. To calculate the tangent, we need the cost function derivative. The result of the derivative is a line with a slope. Basically, if the slope is negative, the weight needs to increase. If the slope is positive, the weight needs to decrease. And that is exactly what we see here. The slope is negative, the weight is too low, and we need to increase it by the slope. Well, sort of, but we'll get there in a minute. First, let me repeat the steps. We know that we need to calculate the cost. This will be a single number. From the cost function, we calculate the error derivative per training sample. The result is a list of 4 numbers. This would already give us some values that would push the weight into the right direction. But we can amplify these nudges by multiplying each error derivative by each input value. The resulting list is averaged and subtracted from the weight. We already calculated the cost. Let's move on to the second task. Calculate the derivative of the cost function. To simplify things, look at the function of one training sample error. To calculate its derivative, we do the following. Take the exponent and turn it into a regular number. Lower the exponent by 1. This leaves to the power of 1. In that case, the power of 1 can be omitted. Take the 2 and put it here. This multiplies each element by 2. We now have the derivative of the error function for one training sample. At this point, there is a list of 4 predictions, a list of 4 targets, and by using the derivative, a list of 4 error derivatives is created. It is important to know that even if the table shows the function derivatives, the thing that is actually stored is the result of the function derivative. In other words, a number. Let me add it to the code so you can see what it looks like. Exit will terminate the program and we will see the error derivatives of one iteration. Let me put the error derivatives in the table. Now we need to multiply each error derivative by an input. The error derivatives are added to the table. And the weights deltas can be calculated. Let's do this in the code. I execute the code. Weight D now contains the changes that each training sample wants to make to the weight. The weight deltas are calculated and now can be used to update the weight. The values are averaged by summing them and divided by the total number of training samples. Let me show you in the code. Let me delete the print and exit statements. Now, the average of weight D will be used to update the weight. There is only one thing I need to do before executing the code. Look at the weight deltas. They are negative. The error function derivative calculates values that maximizes the cost. Of course, we want to minimize the cost, and to do this, we subtract the deltas from the weight. I execute the code. Look at that result. After a few iterations, the network found the optimum weight. I'll decrease the iterations. 10 should be enough. By the way, these iterations are called epochs. I'll create a variable for this. This is very impressive. Our neural network, with just one neuron, just one input and just one output, was able to find the slope of the function in a few epochs. You can see that it doubled x values 5 and 6 with high accuracy. Very nice! By using the mean squared error cost function and its derivative, we went from 25 epochs to just a few epochs to minimize the error. From now on, the cost function is used to indicate how well the network is doing, and the updates to the weight will be calculated separately. Let me show you the process again. Each epoch performs the following steps. Feedforward calculates the predictions for the neuron of all training samples. A cost is calculated over all the training data. The output is a single number. Then the backpropagation starts. It consists of calculate the error derivatives, calculate the weight deltas by multiplying each element of the error derivatives by an input value, and use the weight delta and learning rate to update the weight. This picture shows you the batch gradient descent flow. You will see this picture many times during this training, and each time when the network grows, I'll make some adjustments to it. Our network is getting better all the time. But it has a problem, and perhaps you already spotted it. Our network assumed that the regression line intercepts the y-axis at 0. But what happens if the points are on a line with another y-intercept? How do we change the y-intercept? You will see that in the next part about the bias of a neural network. In the last part, you saw how to use linear regression to fit a regression line as best as we can to the points in the diagram. We assumed that the regression line intercepts the y-axis at 0. But this is usually not the case. The data points can be anywhere in the diagram. If the y-intercept of the regression line is 0, by just changing the slope, the line will never fit the points as best as it can. Let me demonstrate this by moving all the points up. I am going to move the points up. I'll increase each target value by 10. I also update the test target values. 5 times 2 plus 10 is 20. 6 times 2 plus 10 is 22. Let's see how well the network is learning. You can already see that the cost remains high. And also, the predictions are way off. Even increasing the epochs won't help us here. After a few epochs, the weight and cost do not change anymore. This is the best the network can do, so we need a new strategy. We need something to move the regression line up and down to change the y-intercept. In neural networks, this is called the bias. Before I add it to the code, I want you to imagine the bias as just another input to the neuron. But the bias input has a special feature. Its value is always 1. So how can we influence the y-intercept then? For this, we change the predict function. The output used to be calculated by multiplying the weight times the input. With the bias added to the neuron, the output is calculated by multiplying the weight times the input plus the bias times 1. Usually, neural network diagrams simplify this. Since the bias input is always 1, it is omitted in the diagram. And then we write the formula like this. That cleans it up. W is weight, I is input, and B is bias. Let's add the bias to the code. I add a variable for the bias. I chose the value arbitrarily. Later, we will let Python choose a random value. The reason I am not doing this now is because I want to get the same training results each time the code runs. I will use the bias in the predict function. With all the preparation we have done to update the weight, it is now surprisingly easy to update the bias. Look at weight D. It is a list of error derivatives with respect to the training inputs. The bias deltas are calculated in a similar way. You might wonder why I create a list where each element is an error derivative times 1. If you observe this code, you see that bias D will just be a copy of errors D. You are right when you are thinking bias D equals errors D. But for this example, I'd like to create the bias deltas in this explicit manner. You know that the weight deltas are calculated with respect to the input. The same applied to the bias. And since the bias input is always 1, the bias deltas are calculated with respect to the number 1. Let's use bias D to update the bias. I will also print the bias. Let's see how well the network does with the bias added. You can see the cost going down. But we also see that the bias is not nearing 10. Let's add some epochs and see what happens. Very nice. With 100 epochs, the prediction is pretty accurate. And remember, we only had 4 training points to work with. A small recap. We started with a neuron with 1 input and 1 output. This neuron could predict the output, but was unable to learn. We created training data. We made a prediction for each input value and got a result. In the untrained network, the result was not accurate and resulted in an error that was calculated by subtracting the prediction from the target value. We calculated the cost by averaging the errors. We used the cost to adjust the slope of the line. This is called linear regression. Then we changed the cost function. We decided to use the mean squared error and its derivative to have more control over the adjustment of the weight. From that moment, the cost function is used to indicate how well the network is doing, and the updates to the weight will be calculated separately. We found out that our network only performs well if the points are on a regression line that has a y-intercept of 0. So we added a bias that allowed for moving the y-intercept. You saw the importance of tweaking the learning rate and the amount of epochs. When the network did not perform well enough, the epochs were increased and the predictions became very accurate. Let me show you the process diagram again. It's time to update it. I add the bias to the feed-forward calculation. Then, in the backpropagation, instead of just calculating the weight delta, the bias delta is also calculated. And finally, both the weight and the bias are updated. Do you remember the diagram of the cost function? It showed the progress of the cost with respect to the weight. But now we added the bias to the system. With the bias added, the cost function depends on two variables, weight and bias. How do we visualize this? For this, we need a diagram with 3 dimensions. And there it is. You can see how visualizing functions in more than 2 dimensions rapidly makes things complex. And what happens if we add another dimension? Is that even possible? We'll have a look at that when the time comes. But first, we are going to look at something else. Until now, all the data points were exactly on the regression line. Now it's time to see if our network is also able to learn from other kinds of data.